because it's not that much trouble to do so. And if you're here, you probably will never re-listen to any of these things, but at least if you're gone, there's an opportunity. So let's see. One thing I want to get out right off the bat is something you do already know, which is, let's say I have this pipe right here. There's lots of stuff you can do with that material, that member structurally. I could pull on it axially. Notice that's kind of normal to the surface. It's perpendicular. So that's normal force. So we sort of bantered a bunch of these terms kind of around, and now you're going to have to get a lot better at them because we're going to double the number of them. So there's like torsion and axial loading, and you know those kind of words need to make sense to you before we're done with this class. And so that's actually axial right there, and you don't need to know that for this section, but maybe I'll just throw that in right now. And that kind of makes sense because it's like it's the force along its axis. And you can appreciate if you had something small that you could actually pull on it and it would snap in half, right? Now last term we actually had this. That was a part of something we did, but our forces were always vertical, and so there was never any need for any resistance there. We never had to have any structural strength in the axial direction, so we didn't even write that down most of the time, but we're going to need to today. And then last term we also had V. Anybody remember what that stands for? Which is weird. That was on our free body diagrams. That's shear. Shear force. In a sense, that's actually kind of parallel to the cut. So normal is actually kind of perpendicular to the surface of the cut, so to speak. Whereas this one is actually parallel. Have you ever seen that symbol for parallel? So I could put it over here. Doesn't really matter where it goes. And you can appreciate things break that way too, right? And we talked a little bit about that last term, so I won't reiterate that a lot, but it's like I can put force on a pipe that makes it go and breaks in that direction. You'd say, oh, that got sheared off. So torsional force could rip it, shear force could rip it, and then a new one, torsion. This kind of takes some practice to be good at drawing things like this. I've practiced this stuff over the years, so I'm not too bad at it, but it's kind of rotational. So that'd be just twisting something, kind of like you do to wring out a washcloth or something like that. Something can twist and tear.
So I was wondering in the book how torsion is different from like moment. Because moments.
Yeah, super good question. So just to kind of put this in English, maybe I'll just call it twist. I'm not sure that's a very good term. I'll put a question mark there because it's kind of like that's not a technical term, but if you twist something, that's what torsion is. You can break your bones that way. A lot of times it's called a green stick fracture. If you break your leg that way, if your foot twists and your knee is set, then your bone will twist and it'll break really weird. And so torsional rotation. Well, moment, which is the last one, and you already know this one, is actually kind of its desire to, and we drew it in like this, but it's really kind of an object's desire to bend. I mean, I'll draw a picture of it here. It's kind of like bending something. That's why it's different. So it's a twist along the axis. Torsion is this motion. If I have a pencil and I just go like this to it, Indian bird, get it to your little brother. Indian birds are awesome, man.
So if you just rotated the entire thing like that, is that still torsion? Or does it have to kind of both be going opposite direction?
Yeah, that's a good question. I mean, in order for it to cause any damage to it, you'd have to have it fixed over here and then twist it over there, so to speak.
So if you just twisted the whole thing, that'd be almost like a moment. You're rotating.
No, it still would be kind of torsion. I gotta think about that a little bit, but that's still twisting. That's still torsional motion. It's just not being resisted by anything. Whereas moment is like me going like this. It's literally something bending. So this table is moment right now.
Like this.
I'm pushing down. It's trying to bend like this. So it's trying to rotate.
What if instead of just being like this, it's actually going that and twisting?
Say that again? No hard questions this turn.
Because you're saying it's spinning like this in front of you, right? When you're trying to this one's spinning.
Turn it this way.
But can you say that?
If I say to you, that's kind of complicated, I don't want to explain it, that's actually code for I've known it to you.
Can you say that moment is also its desired shear?
No, because shear is literally straight, and you're right in the sense that if you took like a regular wood pencil and you just kept doing that, it's going to go snap at some point, but it's actually the moment motion that's causing it, as opposed to you probably would not be able to do this to a pencil, just go tear it in half, but you probably would be able to do that to something smaller, like a color crayon, probably do it to a color crayon. So do you see how those are all kind of different, I don't know, things that could happen to that shape, if you will? So basically what we got to look at though is, well, what's happening to that thing internally? Now we've already done this a little bit. The shear moment diagrams we made before, we did understand what was happening inside that, and not just anywhere, everywhere. So we found what was happening at shear in different places in it, and what was happening in moment different places, but we haven't really needed normal force because we never had any forces on it that we're trying to get it to pull this direction. And we've also never tried to twist anything before. But you can appreciate in a car, isn't the twist a huge part of that? You got an engine firing, and it's basically creating twist that you transfer to the back wheels. And there is a U-joint in the car. I don't know if you know this or not. There's a U-joint in the car designed into it to actually snap so that something more important doesn't break. There's weaknesses built into all kinds of things, so that if you do, ask your wheels to do too much work by peeling out 50,000 pounds on it, so to speak, it doesn't like break the engine. It breaks some part that costs $10, which is actually awesome. It's a brilliant idea. So the U-joint is designed to do that, be a break point, but it also lets you change direction, because usually an axle has to be straight. But what if it comes out of the engine and then the wheels are a little higher? Well, it can actually kind of be a different angle, and it can still, this rotation is connected to that rotation. So U-joints can also do that. So the point is, there's real twisted motion that can actually break stuff, and you can appreciate what that would look like with metal. If you had something strong enough to just really twist it, it'd be kind of cool to look at all the weird lines it would create. And again, your book does a great job of looking at one microscopic chunk of a piece of metal when you go twist it and kind of think, how do we describe what that is, or how do we say what just happened there? That kind of a thing. Okay, that's a decent introduction. Let's do first some easy problem. Oops, that's the wrong world. That's the right world. Seems like you should start with number 4. You should be able to do this right now, but let's just get our feet back underneath this. I'm going to go kind of quick here. This is not a shear moment diagram, because they say the shaft is more supported by, and let's just stop and look at this really quick, a smooth thrust bearing. What the heck is a thrust bearing? Well, one of the sheets I gave you shows what a thrust bearing is. What kind of support does a thrust bearing provide according to that sheet? And this is in your book too. I just copied it and got it out of your book.
A Y and an X.
It's not a Y and an X, I don't think.
Yeah, the thrust bearing, the journal bearing is the one that goes up.
Have it backwards. Oh yeah, there's both. There's a thrust bearing and a journal bearing. So A is a thrust bearing. B is a journal bearing. Take a quick look at the drawing. Do you see it actually drew it correctly? In a sense, a journal bearing is just where you slide something through it, but it actually can move in there. But what it does is, if you do want to spin something and you want to keep it in place, like if I try to spin this pencil, it's like flying out of control, right? It's like, I don't want it to fly out of control. I want it to stay right there. So I kind of squeeze it right here. But notice it can move. It can move left and right. There's nothing stopping that. So do you see how it says there's only one resisting force there? It's vertical for a journal bearing. But then for the, did I say that wrong?
Yeah, no.
Yeah, for the journal bearing. But the thrust bearing has like a couple of pieces of metal on both sides that don't let it slide very far. You still don't want to have a lot of friction, but if you kind of put a ring around both sides of it so it can't get away, well, now it's actually got the ability to resist forces left and right. We don't actually really have to know that for most of the problems, but it's just kind of cool to stop and think about for a second. But notice they say determine the resultant internal loadings acting on this only at C, not everywhere, which is what we did for a shear moment diagram. But they say determine all the loadings, plural, like what's happening everywhere. And that list I just gave you is the list. We need all four of those: normal, shear, torsion, and bending moment. And this problem, though, is still, if you will, pretty much two-dimensional. This is not a three-dimensional drawing, and so this is not new to you, ultimately. Now, one thing I do want to do with this question that I'm a little hesitant to do, every single time we did this last term, we did it on the left-hand side. And I'm going to do it both ways this time, just to show you that you get the same answer. But you may remember, in order to do this, the very first thing that you've got to do is come up with the reactions at the supports, which in this case would be at A and B, those two. That's what's keeping it there, right? Because I mean, if I've got 900 and 600 going down, that thing is not going to stay static unless A and B are pushing up. Now, is it automatic that A and B are pushing up? Are they both pushing up?
Yeah.
Maybe is the answer. Watch this in this picture up here. If this wasn't 900, but it was like 900,000 or something like that, can you appreciate what would happen is this would want to fly up over here? Because it would pivot over this and fly up in the air, in which case this force would actually be down. Actually, you'd be holding it down. So it's not quite so obvious here. We're actually not sure. Our assumption would be, because there's 600 down and 900 down, that they're both, working together to stop that. But if we end up with a negative number, it means, oh, I guess that's not the case. And notice, because that force is outside the axle of this, that could actually definitely could happen. You see what I'm saying there? So just to keep myself, I don't know, you tell me, do I need a free body diagram for this if I'm in lazy mode? Yeah, so notice I'm going to assume the forces are pushing up at both of those, and hopefully I'm right about that. And then, of course, I got 900 newtons over here. And up to this point, I'm thinking I didn't really need to do this. I'm just being lazy. I could have been lazy and just drawn those forces over in the picture. But remember, the 600 newtons per meter, notice it doesn't say 600 newtons. You can't have a unit 600 newtons and a bunch of arrows saying it's that way everywhere. It's 600 newtons per meter. I've got to reduce that to just one force, or I'm going to have a heck of a time figuring this out, because that's actually a billion forces. Well, notice that's over a distance of how far? 2 meters. 600 newtons per meter times 2 meters would be 1,200 newtons. And because that's a rectangular force, I would know it's exactly in the middle of that. It's right at C. Do you agree with that? So,
and also on A, you also have the X direction.
that's right. And this is exactly what we ignored all last term. So I should, in a sense, go in here and draw, I should call it, I'm going to erase this, but I should call this the force of A and Y and the force of A and X. But do you notice there's no other arrows going left and right here? So therefore, the force of A of X is going to be 0. So you're absolutely right. I should be including it. And that's kind of what we did all last term. Like, we just never bothered to even draw it in there. But if there were forces acting on that, then I would need force of AX might actually need to do some work here, right? So I think I'll leave it in there just since you mentioned that, and I'll go ahead and rename these. So in a sense, I kind of did need to draw a free body diagram here, thanks to that kind of distributed load that we see there. And so now I can do a sum of the moments calculation to figure out how much of that 1,500 newtons. Oops, I screwed up here. What did I screw up? I'm stalling, giving you time to answer the question.
Are you talking about the distance?
No. That's 1,200, because it's 600 newtons per meter times 2 meters. It's 1,200 newtons that's up there, not 600. So I replaced that 600 newtons per meter for 2 meters, I replaced it by one force in one location and I put it right in the middle. So it's actually right at C. You see what I'm saying? So this is right on C, which happened to be right in the middle. This is B, and over here, this is D. So now my free body diagram is actually good. And we saw last term that it's not going to do me any good to do the sum of the forces in Y, because I just know that those two have to work together to defeat 2100 down, but I don't know how much goes to each one. And so that's going to be a dead end. Whereas the sum of the moments is going to allow me to actually answer this question. So I don't know, I have no reason for this, but I'm going to say the sum of the moments around A would be, let's see, would be the force of B in the Y direction. That's rotating it counterclockwise. And I didn't redraw the distances because I can steal them from over here. 1, 2, 3, 4.5. It's 4.5 meters away, and that's positive. But 1200 is trying to get it to rotate clockwise, which is negative, and that's a distance of 2. And 900 is also trying to get it to rotate the opposite direction, and that's a distance of 6 meters. And that's it, and I need that not to rotate. True? Not new. And so, to save a little bit of time here, I'm just going to answer these questions. So the force of B and Y, then if you crunch that into your machine, since I already did this before class, is approximately 1733. And then I could actually switch to the sum of the forces in Y being 0, and I could say we have 1733 pushing up, we have 1200 pushing down, we have 900 pushing down, and I'm assuming anyway, we have force of AY pushing up. And indeed, that does come out positive, and I get about 367. So first of all, does that make sense? Like, why B is working harder? B is working way harder, 5 times as hard. Why does that kind of make sense if I look back at the picture?
Well, it's kind of like that 12 was almost right in the center, 5 off. And so if you want to think about it, like 600 might go to A, and so around 600 would go to B, plus the 900.
Yep, that's exactly right. It's a great way to say it. The 1200 is, roughly in the middle between, get bigger. So it's like 600 of that 1200 is held by force of A, and 600 is held by force of B, but then 900 is like all on the B, right? So it's like, yeah, I guess that would make sense that it's way bigger. So at least that seems reasonable, kind of in hindsight. And again, I didn't rounded those to the nearest whole number or something, so whatever, close enough. And so now I actually am in a spot where I can now section this thing off and find out what's going on inside. Again, internal is the key word this term. I can find out what's going on inside that any place I want to know. And so fortunately, instead of saying, find out everywhere, which again, does it make sense? You'd actually need to know that. We don't want that rod to break. So we really need to find out the worst place for all these things to happen. That's where we really need free body or shear moment diagrams, but they're taking the pedal off a little bit and just picking a spot. So let's do now these internal loadings. As always, interrupt immediately when you have questions. And they asked us specifically at C, and so cool, I can do that. But let's do this first the way we always have done this, which is left. And by the way, would you agree the left side of C looks simpler? Like there's less going on over there? If I'd like to be done, the left side of this actually seems better. And so I need a free body diagram of the left-hand side. And now I'm in a spot where I can actually draw that. So I can say, I'm going to chop this thing right here at C. And I now know over here at A, the force of A is 367 pushing up. And so that's why I needed to know that from earlier. That's why I had to get that reaction. Otherwise, I would have said there was nothing there, but there is something there. So I got 367 there. Let's see, what else do I have? What's my free body diagram missing? Yeah, and I notice over here, like I'm only talking about from here to here, right? So I got 600 newtons per meter, but it's only 1 meter. Therefore, I got 600 newtons, and it'd be right in the middle of that. Does that make sense? So it'd be like 1.5, it'd be 1.5 over. Because the stuff that's on the other side, I don't have that. It's not there. It's not on this left section.
Resultant force of 600 newtons applied at 1.5.
Yes. And so maybe I'll draw that in there just because it's not that obvious, but that would be 1.5 over to that location, since it would be right in the middle of that section right there. Now you can see clearly that the forces here are not going to balance in the y direction, right? Because you got 600 going down and you got 367 going up. And last term we said, and this is where you've got to draw in all those 4 forces we talked about at the start of class. And let's not be lazy. Let's draw them all in. We said the conventions were shear force right there goes down. Moment goes this direction. Let's see, what were the other ones? Did I save this? Yeah, we got torsion and we got normal force. Sign conventions. I gave you this last term. I don't think I reprinted this, but I just want you to look at this for a second. It's not a super important idea because when we go to 3D, it's going to get hard to keep it straight anyway. It actually doesn't make any difference which way we draw this. We just like to get the same answer, whether we section it to the right and the left. That's what these sign conventions are really for. So notice, didn't we just ignore this whole thing last term, the normal force? So because I have a section over here, my normal force is pointing to the right, if you will, and then torsion wasn't on this. So what are we doing? 1244, lost 4, this one. So there's actually a normal force here. And you can tell right now that that normal force will be 0. That's why we kind of left it off. This is just like last term. There weren't any vertical or any horizontal forces here. So I could right now say that force is equal to 0.
Doug, I was kind of getting backwards. Don't we have a left side, so should the normal force go the other way?
Well, that's what the sign, normal force is just normal to the cut. And it doesn't matter whether you draw it left or right.
Oh, okay.
It's just a convention that if you draw it right on the left hand, when you're making a left-hand section, that if we switch that when we do the right-hand section and draw it left, then we'll get a positive answer both ways. If you screw it all up, one side you'll get negative 300, the other side you'll get 300. And so again, there's no such thing as negative numbers really. And so that convention is just to keep you from getting all screwed up. Now it does make a difference because if I try to crush this pen in compression, that's very different than trying to tear it apart in tension. That's 2 different materials sometimes. So it's not that that doesn't matter. It does matter.
So the normal force we just drew is kind of like compressing as opposed to.
In a sense, I'd say it's more like it is pulling it. It's taking that right side that we just broke and kind of pulling it in this direction. And so if N was 7, then we're in trouble because we have nothing else to resist it.
Well, A would have to resist the force bearing.
Yeah, now good point. If there was some normal force on it, then we do have a bearing there that could resist that, right? But if we were on the other side, it would just pull right out of there because there's no force in that journal bearing, right? So that's kind of interesting to note. But in our case, there's no forces anyway, so that's awesome. And then there won't be a torsion either, but I think I'll go ahead and draw it in. There will be in later problems we do today. So do you agree there's no forces trying to twist that? And you should even be thinking what kind of force would twist it. I can't even understand what would even do that. You know what I mean? But what would do it is if that wasn't something circular, but it's like this book right here. But what if I had a vertical force on it that was way over here? Like, isn't that trying to rotate it now? So then that would twist it. But we're seeing, right now we're just doing kind of a 2-dimensional problem. And So just in interest of time, I'll say, okay, that means normal and torsion are just going to have to be 0 because there's nothing causing them to do anything. And then we're just back to what we've done before. And so let's just super quickly do those. And so I could say, okay, great. Well, then the sum of the forces in Y is a good place to start here, since I've got 367 going up and I've got 600 going down. And now I've got, and again, do you understand why you're able to put that there? Because do you agree that because just from last term, the end of that piece of material over there that I kind of chopped is connected to something. If there was nothing there, if that was literally the end of it, then there's no shear there. But it is connected to something that is not wanting to let this thing go up and down. And that's really the question is, will it be able to do that? We're about to come up with what that number is, but the question is that material internally able to provide what you're asking it to provide? The answer is, and that's the next section, is not necessarily. And so I called shear as downward here, which makes it negative, and that's it. That's the only vertical forces. And so that leaves B to be negative 233. And so that just sort of means it's like, oh, it's the other direction. Now, that doesn't mean we necessarily need to turn it around. It just means that, what's it holding it from doing? Is it holding it from trying to go this way or trying to go that way? That's all it's really saying. And actually, in the case of shear, it doesn't make any difference at all. 233, it really makes no difference at all. And then the other annoying thing about this is, what's the label for that in this problem? Newtons, which is not good because we have an N for normal and N for Newtons now. So it's like, can't you come up with some other letter? And so that's kind of cool that I was able to use such a simple algebra equation to determine that. But again, as I mentioned before, it's like, okay, well, that connection that's made internally right there at that location in that piece of metal, it better be capable of handling 233 Newtons of shear, or it's going to shear off right there. Now, of course, in the picture, that looks like a weird place for that to happen, doesn't it? Because it's kind of in the middle of nowhere. Shear usually happens like right over here, where it's actually being pushed up on. And then right next to it, you got stuff pushing down, and it's just like, then it would slice like scissors, it's going to slice off. Okay, so of course, to get M, which is a moment, we're going to have to do some of the moments. I hope this isn't brand new to you. Some of the moments and around C might be a pretty important distinction there. And so we have M, which is, notice, drawn positively, just like V was drawn negatively, oddly. M is drawn counterclockwise, so that's positive. And then what else do we have happening around C? Well, we have that 600, which is also trying to get it to rotate positively, isn't it? And it's a distance of how far away? How much? 0.5, that's exactly right. 0.5 meters. And then we have that 367, which is actually trying to get it to go the other way, which is kind of good because we don't want this thing rotating. We can't have all of them be positive. So it's trying to get it to rotate the other direction. Unfortunately, it's further away. It's 2 away. And that's all of the desires to rotate that are on that shape. And again, you have to see this as some location inside the middle of it that wants to snap in that moment direction, snapping off this way, not torsion. And so if I don't blow that, I get 434 approximately. 434 Newton meters. Newton meters. And so there's all 4 of the internal loadings. And then again, in the real world, we'd go pick a proper material to handle that load. But what I want to do now just quickly is like, let's go do that on the right-hand side and see if we can get the exact same answers. And I only say that just so that you feel comfortable choosing whatever side you want to make it easy for you. All last term, I chose the left side every single time. But what about the right side? I think I'm going to be lazy and try to squeeze this all into one. And I think if we switch colors, we can get away with that. What about the right side? Well, what's the free body diagram look like on that side? Well, we'd have our cut over here. And we've got 900. Remember, the left side didn't even know there was a 900, right? Didn't even know that was there. We've got 900 there. We've got that force of B pushing up, which we figured out a while ago was 1733. And then we've also got some of that 600 over there too, and it's actually right in the middle of C. And so just like last time, it's 600 times 1 or 600 newtons. So it's kind of like right there. So do you see why this side's kind of worse? Like that's why the left side would be better. But the point is, can we get the exact same answers? Now, according to that sheet of moment now goes this direction, shear goes up instead of down, which we never even had to stare at last time. And by doing this, we're actually going to get negative 233 again. If we drew it down, we'd get positive 233, and that'd be fine too. That's why somebody thought, oh, let's just have some conventions about this. And then the moment, instead of rotating in the counterclockwise direction, is actually rotating in the clockwise direction. Yeah, and the normal goes to the left instead of to the right. And torsion is still torsion, but I'll go ahead and draw it in here. We don't really need torsion right now, so we'll get into that a little bit later.
Does it matter, not matter, if the arrow's pointing counterclockwise or clockwise with torsion?
We'll talk about that because that's the right-hand rule around which something rotates. So when we go 3D, we'll have to get that back, be able to do it. Good question. Okay, well, cool. So again, just like last time, N and normal force and torsion force required are both 0. So that was not very interesting since this isn't 3D and so forth. But what about these other ones? Well, some of the forces in Y. Let's see, well, what happens to shear then? Some of the forces in Y. We've got 600 going down. We got 1733 going up, 600 going down, 900 going down, and notice V is drawn up, so that'd be plus V. Punch that in, you get V is negative 233 again. Now I'm doing a little rounding because that wasn't really 733, it was like 733 and a third or something, and so this actually could be off a little bit, but I don't think it is, but it could be. So you get the same exact answer again. So it's like, oh, cool. Isn't that interesting that we could slice it and do this calculation from the right and get the exact same answer? Yet all the inputs are totally different. Like last time we had a 367 in that calculation, and this time we have a 1733, and yet somehow it comes out the same answer. Isn't that kind of weird? Kind of cool. What about the sum of the moments? Also around C, what happens to those? Well, I've got that M, but notice that's negative now. Does that make sense? It's like that's the negative direction, right? Clockwise. I've got 17. I always like to start with positive ones. I got 1733 that's trying to get it to rotate clockwise. And let's see, how far away is that from C? It's 1 and 1.5, so it's 2.5 away. So that's trying to get it to rotate positively. The moment is trying to be the internal member, the internal connection is resisting that. That's why there's a force there. It's trying to rotate it negatively. The 600 is trying to rotate it negatively, and it's 0.5 away. And the 900 is trying to rotate it negatively. Did I screw any of those signs up? And that's 4 away. Did I do that right? I got in kind of a hurry there, so I could have screwed up a sign really easy, I think. Answer is no. Wonder of wonders, totally different looking equation than this previous one up here. All different ingredients, looks totally different, yet what does it produce? Exact same answer. Punch that in just to double check. It even gives you the correct sign. Last time it was a positive, it gives you a positive again. Do you at least see why somebody thought the sign convention thing might be worth doing? Because it made us get the correct answer to this question. That's kind of what it comes down to, at least the same answer we got before. Remember, the negative shear does tell you something. It just tells you what direction, its neighbor that it's connected to. Is it helping push up or push down. So it's kind of cool just to see that you can get the same answer from both sides. So in this problem, I would have chosen the left because it's way easier. What'd you get?
I'm getting 432.5.
Yeah, which is just rounding,
Oh, right here.
because that's not really 1733, it's 1733
Right.
and a third or something like that. So it's rounding. Because I was lazy about that previous calculation. If you run this first calculation up here, this one, you don't get 1733, you get 1733 and some change. Please be bothered, continue to be bothered by stuff like that. So here's an extra credit opportunity after, we're going to do this one. Want to do this one really quick, which is also one we did last term, but I'm only going to do it from one side, and I'm going to do it from the hard side, which is the side you're comfortable with, the left side. So this is a triangularly loaded beam. Let's quickly get the reactions at A and B. And I am going to be lazy here. Maybe I'll change my mind and think this was a bad idea. But in this case, I think I'm notice the supports are out all the way out at the ends this time. So I'm sure both of these are actually pointing up. So I'm just going to call that the force of A and the force of B and reuse this diagram. And then remember, just like last time, you've got to replace, do you remember this from last term? How do we replace a huge triangular load? 4 newtons per meter on one side, all the way to 4,000 actually, 4,000, see the little K there? 4,000 newtons per meter on one side, all the way to nothing. How do we replace that? Yeah, 4K times, and notice it's, actually, I think I'll write this in. Newtons per meter times on the bottom 6 meters times a half. It's times a half because that isn't a rectangular load. Marty, my dumb old bald high school buddy. Okay. So that's 24 times 2, which is 12. So you have to have 12K. That's your single force to replace all of those. Where does it go? What is it? Yes. Newtons, because the meters cancel. Well, it's right now it's, yeah, I see what you're saying. Yeah, it's a third from the left or 2/3 from the right. So it's kind of like over here somewhere approximately. And I've got force of A pushing up here and force of B pushing up here. In the interest of time, I won't redo that. I'm just going to tell you the force of, I'll say the sum of the moments produce. Force of A carries the majority of it. You can tell from the location of 12K, it turns out force of A is 8K and force of B is 4K. And we didn't, I mentioned this a time or two, but it's actually not a coincidence that that's also 1/3 and 2/3 of 12. So out of laziness, or if this happened all the time, you wouldn't actually have to do that moment calculation. You could just say, well, I can see it's closer to force of A. And because it's 2/3 of the way over, then it's 2/3 of the weight of 12. If it was just a triangular load. And so cool, now I'm ready to find, in this case, they said, what's the cross section? Tell us what's happening at section C. Not everywhere, way harder last term. Why did they say this last little statement, assume the reactions at the supports of A and B are vertical? Yeah, looks like it's just kind of sitting on top of an I-beam, and if you didn't assume that, there could be a vertical force that would want to push it off. Like if they really were just sitting there, then you better make sure there's no sideways forces or it's going to tip over. Like then you better weld it or bolt it or something like that, right? So I could have not read that and been okay, but let's figure out what C is. And so I'm going to do the left side, which is the hard side. And if you have a penchant for extra credit, you're gonna see if you can get the same answers by doing it on the right side, but I'm just gonna do the left. So the internal loadings. Internal loading at C. I'm only going to do the left side. And I'd like you to stop and think about this for a second. So I'm going to just quickly draw the picture, but this is actually really hard. And it's part of the reason I chose to do it kind of again, because when I did this on the test, I actually drew that triangle the other direction. If I'd have drawn it this direction, you would have suffered hard on that test. And I'll show you why right now, because you're probably used to just doing the left every single time. And so let's see what happens as a result of that. So if I got my little free body diagram going here, because I am chop. And I figured out 8 is pushing up right there. You see what the problem is here? Like, what's the load there? Because stop and look at this picture that's back over here. What I really have is this, well, trapezoidal load, don't I? And because I turned that around on the other test, you didn't have a trapezoidal load, you just had a little triangle, and it wasn't so bad because it's still just a third. But what are you going to do with the fact that you have a trapezoidal load over there? You can see that the load on the left is taller than the load on the right. So maybe it's like right here. Does that seem about right? Yeah, so the secret to this is actually to split it into a rectangle and a triangle, and frankly, just to do them separately. So the problem is you don't know how tall the rectangle is. You agree with that?
Wasn't it
4 is this entire height right here. But it's like, how do I, so the 4 is nowhere now. Like the 4 doesn't exist anymore because I just chopped it into 2 pieces. So is that like 3 and 1? Is it 2 and 2? Is it 2.5 and 1.5? Like what's the split, if you will, between these two? Because I need both of those now, don't I? Don't I need like those 2 separately? Well, let's just do this with basic math. Here's the easy way. We could find the equation for that line, which is kind of what we did last term, but let's just do this the easy way. Let's say that little distance right there is x. Since the original entire height of this thing was 4, couldn't I say 4 is to this entire length down here, which is 6? Couldn't I say 4 is to 6 as, and so that's the big triangle, as x is to what? 1.5. So hey, I just set up a proportion. So I solved it. Times 4 times 4, it's 1. So I got x is 1. And if I know x is 1, then I know that this down here must be 3. Does that make sense? Because 3 plus 1 is 4. So now I know how tall the rectangle is, and I know how tall the triangle is. Does that make sense?
Well, that's the hard part. What's the one extra credit now?
Yeah, so this side is the hard side, which is why I'm kind of doing it for you. And so what do we have then? If we look at the triangle and the rectangle, the difference. So how much weight is there because of that rectangle?
3 times 1.5.
Good. 3 times 1.5. So what is that? 4.5? And that's right in the middle of that, right? So 4.5 right in the center of it. And then I got the triangular force, which is 1 times 1.5, which is 1.5, but then I got to cut it in half. So it's 0.75.
Oh, yeah.
You agree with that? I'm talking fast, so
Say that one time.
Yeah.
1 times 1.5.
yeah, so
times 1/2.
So the 4 times the distance.
yeah, so this distance is 1, this distance is 1.5, so I multiply 1 times 1.5, but because it's not a rectangle, I got to cut it in half because it's a triangle,
Okay, yeah.
which by the way, when I was doing this, like at my desk yesterday, I forgot the 1/2 and looked in the back, it's like, wow, why is it wrong, you know? It's like, this happens to me too.
And it's 2/3 of the way from the short side.
Exactly, it's 2/3 of the way from the short side. So and I think I'll draw those in. So because our whole distance is 1.5, then that means this is 0.75 to here. Does that make sense? And then this 0.75 over here is 1/3 of the way over. 1/3 of 1.5 is 0.5, so that makes it 0.5 from here. Do you agree with that? Is that too fast? Like that's where those are?
Would it be smart to combine those two?
I don't think so. I think
Or
it's too much
many
trouble.
racks?
I think it's too much trouble. It's a waste of time. There's only 2 of them. And I'm gonna have to do a bunch of work to do that. And it just means when I do the sum of the moments, I just got 2 things to add instead of 1. So I think it's more trouble than it's worth, but you're absolutely right. I could turn that into, and probably there's some formula where I could even figure out where is a trapezoidal load? Is it like 2/5 the way over? Or, you know, is it some formula that relates the tall side to the short side, so to speak? Because do you agree that the tall side of ours is 4? The tall side is 4. And the short side is 3, and then this is a distance of 1.5. And so is there some formula that would tell us like where that single load is in some way that I could turn it into a single load? Again, that sounds like a great extra credit problem if you have a lot of time on your hands, but I would,
In the back of the other book, had a bunch of examples.
yeah, there might have been a trapezoidal one in the back of that last book. So that's interesting. Again, if I was doing that all the time, and coincidentally, last night, 8 o'clock, I was home making money, drawing house plans, to having that exact discussion with an engineering friend of mine, because we were trying to get a beam to work in a house that was already built. And so the beam was already in there and we were trying to get it to work because they loaded it weird. And so we were just having a conversation about that, trying to get that to work. And it's the first time I ever attempted a trapezoidal load using that BC Calc program. And I did what I thought made sense, and I called my engineering ex-student. So, and he's like, yeah, you totally got that right. So, all right, yeah, right. Okay, so let's see. Then we said on the left side, I'm going to draw this in a slightly different location. We said the shear is there. We said the moment is here. Like last time, the normal force is here and torsion is here, but those aren't going to produce anything. So torsion and normal are both 0 again, because these aren't that complex of problems yet. But we're going to get answers to the other 2. So let's see if we can get those now. So the sum of the forces in Y seems like an easy place to start, because I got 0.75 going down. I've got 4.5 going down. Ooh, and I've also got, I got 8 going up, and then I've got V going down. And if you do that, and you also remember, I'm being lazy. These are what are the units of these? Kilonewtons. They're not just newtons. You end up with V equals 2.75 kilonewtons, or 2,750 newtons. So that's, and watch this too. This is just kind of a good thing to get used to, but it's like, instead of just saying V, I could say V of C, because that's like the shear at C, right? It's not just anywhere, it's the shear at C, and this is the torsion at C and the normal at C. I mean, that's probably a good idea. If you look in the back of the book, I'd be willing to bet that's what it would say. It's not just going to say V. And then what about this moment? So notice these calculations aren't hard. The hard part was getting that trapezoid sorted out, right? So what's the normal or the rotational desire around C? Well, I got M trying to go positive. I've also got 4.5 trying to go positive, and we said it was a distance of 0.75 away from C. I've got 0.75 as a force trying to get it to go positive, and it's a distance of 1, I think, off of there. And then I got 8, which is the only thing negative. 8's trying to get it to go the other way, -8, and it's the furthest distance, 1.5. And so I get, and that all has to be 0, and I get the moment as about 7.88 Newton meters, weight 7.88 kilonewton meters.
What do you?
7.875, I think, or something like that is what you actually get. So it's much easier from the right side. You should have done this from the right side, but I've spent a little time on the right side of these problems just because I'd like you to get comfortable with that. These were things we did last term, but go see if you can get the same answers from the right-hand side for extra credit. And again, turn that in. That's the kind of thing that allows me to give you a boost at the end. I think Thomas got an A last term because of stuff like that. So kind of close to the line, and because he did some of those, bam, got an A.
Problem, guys. You got enough extra credit to pull it out.
Oh, that was scary.
I don't think I told you guys, Doug was like, you really spazzed out on number 2, and I just got like 10 wrong on number 2. And I aced the rest of it, but I ended up with like a B- on the test just for that one.
That's all you needed. So that's review-ish, but with a little flair to the right-hand side. I would highly recommend you do that just because I really do want you to get comfortable with the other side. You now have the right answers, so you should get the same answers or you blew it.
Well, I have two of the answers already. Can I get as much credit?
What answers?
The torsion and the normal.
Yeah, you already, I'll do the torsion. Let's split the work up. I'll do those and you do the, I like how you think. Okay, so let's go into some deeper water now with number 16. No, wrong, not doing number 16.
And
We're doing 18. Did I bring 18 in there? Uh-oh,
This is what nightmares are made out of.
we're doing 18, but I don't have 18 downloaded, so I'm gonna have to go do that really fast here somehow. So what's different about this picture? It's like the same thing. You just got some bars there's a bar with a couple supports and then you got forces on it. But what's different about it? It's never happened before.
have 3 axes.
You see how the fact that you got some forces kind of pulling sideways and some pulling down. And of course, you can appreciate with this being some kind of a chain driven, I mean, your car is like this, that we've now got forces pulling some other direction. This is no longer possible to do as a two-dimensional problem. Does that concept make sense? And so what's kind of tricky about this is you got to really do a good job drawing, because now you got shear forces going more than one direction. It's not just down, it's like down and sideways. And so we got to really think about this. Let's see, what do they tell us? Shall be supported bearings by 2 bearings A and B subjected to the forces. And so because of that, the way that's connected, does it make sense? It's being supported vertically. So I'm going to draw this in. There's a force at A. What direction is that going in though? Yeah, we're having to assume that this is a thrust bearing. Well, I guess we don't know. They didn't really tell us. But remember, there's no forces going axially along it, so we kind of don't care. There's not going to be a normal force here either, but there's going to be a torsion for the first time. Well, not really. There's not going to be torsion, but whatever. Anyway, so that is actually in the Z direction. So what's hard about this is we're going 3D. The good thing is you don't have to learn anything new here. You just got to be a little more careful about looking at what's happening here. So I do have a force going down of 400 newtons. Well, 400 newtons is. And so can you see how that force of AZ is going to push up and defeat that, so to speak, on that side? That's why it goes up. But is that the only force that bearing provides because it's wrapped all the way around it? I would say no. There's also, let's see, I guess I'll draw it over here. There's also that force. What direction is that in? Notice that's over here in the Y direction.
It doesn't say what kind of bearing it is. So
Yeah. Now, because of the way it sticks in there, does it make sense? Those 2 forces are for sure, but what we don't know is there a force of A in the X direction? If it's a journal bearing, which just slides through it, then we'd say, no, there's not one. And they didn't tell us that. But in the end, we don't care because notice the forces that are pulling and pushing on that aren't trying to go in the X anyway. So we don't even care in this case, which is kind of interesting. And that's apparently, and again, this guy's a pretty good author. That's apparently why he didn't tell us what kind it was, because we didn't really need to know, I guess. He just said bearings, but the picture shows that it would at least do those 2 things. And of course, the same thing is going to happen on the other side. But notice I had to give that kind of a complex name. Come on, man. And so the same thing is going to happen over here. And again, I don't exactly know how I want to draw this in, but I think I'll draw think I'll draw it over here. I'm assuming that this force at B also in the Z direction. I'm assuming those two are going to work together to handle that. Well, what is that? It's a pulley. Is that 400 or is that 800? It's not obvious, is it? But it's like force of A and Z, force of B and Z are both going to work together to handle what is 800 is the answer to that. Now there's only 400 newtons of tension in the cable itself. And I'm always thinking about this at the gym the other day too. I was sitting there huffing and puffing and I was staring at this one that just had wires going all over the place. And I was like, wow, what is that? And I was realizing, well, I just curled 70 pounds 20 times. Therefore, that's not 70, it's 35. So I was getting, because I can't curl 70 pounds 20 times. Some of you guys might be able to, but I can't. And then I looked at the way it was, routed over it, and it was exactly this. There was pulling down in two different places. And so that's actually 800. It's only 400 in the cable, but because it's pulling down both, it's actually 800. And notice there's literally two arrows aiming down at 800, so it's 800. And clearly force of AZ, force of BZ are going to defeat that. And also force of AZ is going to do more of the work, right? So of that 800, maybe 700 is AZ and 100 is BZ or something like that. But then you also have the two 80s and 200s, and they're both pulling, now I don't even know how to talk about it, like right, what even direction. But notice it is assumed, and I'll go ahead and add this into this picture, it is assumed that this is the positive Z, the positive Y, and the positive X. It doesn't matter, but just because they drew it that way, that's kind of the way maybe we'll need to know that. Because 3D is not so clear anymore as to what's positive and negative, so you kind of got to define it yourself. And so apparently the force of AY, and then over in the other one, the force of BY. And by the way, notice I'm drawing these backwards. I actually don't know why I'm doing this, but I was kind of drawing those negatively. But the reason I drew them that way is because I can tell that's the direction they're going to go. You understand what I mean by that? Yeah, they got to push against the 80 and the 200, right? So I'm just using my brain to say they must be going that way, and that way they're going to come out positive, and I won't have screwed up the way I drew the arrow. Do you see how there's no sign conventions here anymore because it's like too confusing? But in this case, I'm able to reason it out for myself, and so I think this is actually going to work. And so I have to do what I always had to do, which is to start this out by the reactions at A and B. But it's kind of mind-blowing now because of how much stuff is going on there. And so the only advice I would give you with these is make sure you're really careful to draw your lines correctly parallel. Like Z is straight up, and so I was careful to draw force of AZ and force of BZ straight up. And then I tried to draw force of AY and force of BY parallel to the y-axis, because you're trying to draw 3D here, and it's just not going to work so good. And so let's see, how do I say this? Does it make sense I can't do the sum of the forces in Z?
I just wrote it down. I was like, I can't do it
Why not? Why can't you do it? Say it out loud.
because I have FAZ and FBZ.
Yeah, they're going to work together to defeat that 800, but because they're proportionally in weird locations to each other, just like before, I'm not going to be able to make any headway with that. I'm going to have to do with some of the forces, some of the moments. And so let's try to do that. But here's the interesting question, my friends. What do I call this thing?
The moment was my fear because
The sum of the moments I'm forced to, just like we were in previous problems, but it's like around what? Before it was just like around C, some location. But do you agree that those forces are trying to get that AB pipe to rotate all kinds of different directions? It's like it's got 3 dimensions of, so now it's just not like, you can't just say around A now. That
you have
doesn't
to
work.
limit like 2 dimensions. So you have to say moments around A and the XY plane.
So you got to think about an axis. When something rotates around, like I'm going to go over here and rotate this. What axis am I rotating this around right now?
Y and,
It's like that.
Oh, the
axis.
X.
It's like a line that's going this way, right? If you don't have to name it, but it's like it's a line that's going this way, right?
Yeah.
But what if I decided to rotate it like this? Now what axis is it on?
Z.
Now it's on this axis, right? So we got to pick an axis. So we can say some of the moments, but around what axis is it rotating? Before, we never really had to think about that. But if I rotate this table around that axis, so to speak, before it was just a point, like we just said, oh, it's a point right there. But there actually was a line there, like we just didn't have to think about it. Well, now you do. So what axis would these forces, and let's consider the 400. What axis is the 400s trying to rotate around, the X, Y, or Z? You need to be able to see that.
The Y.
Connor suggests the Y. 400s, is that going to cause it to spin around the Y axis, as Connor said, or is it actually the X or the Z?
Oh.
It's one of them. He's right. It's Y. Do you see that? Can you imagine it spinning just the 400s? I'm only looking at the 400s.
And that kind of, so the 200 and 800.
Yeah, what are the 200 and 800? What are they spinning it around?
They're spinning around
It's the Z.
the- So if you do moment around Y, does it cancel?
Or
Or
is
sorry,
that how the right, would that be the right hand rule since it's?
Yeah,
is up,
that's exactly
so
right.
it would be positive?
And so when you say, now when you say Y, you say, oh, okay, if it's around the Y axis, there's the positive Y, that's my thumb. And so rotation in this direction is positive.
and then do those, it just kind of ignores those 280s, we just have to ignore those.
Exactly, because they're not causing the desire to rotate around the Y axis because they're parallel to it.
So whatever it's perpendicular to, that's the
Yeah.
axis it's gonna be spinning around.
That's exactly right. It's got to be perpendicular to that axis. So isn't this like, it's
Yeah.
actually not new, but it's very
Maybe
painful.
momentum around the Z axis. Oh, no, that still gives you the momentum around B. and Z axis.
So because of the right hand rule, that is positive rotation. Again, your thumb goes toward the positive axis. And your fingers point to positive. You're tracking with that, okay? Now, again, the only reason we care is we have different forces trying to get it to rotate different directions. And if we get those signs wrong, it's going to make us get it wrong.
Thought I was done
So-
doing this in tests. First it was physics, now it's strength materials.
Gang sign point.
Okay, so we're doing momentum around Y.
Yeah, so what I'm going to label here is the sum of the moments around Y. It's around an axis, not around a point now. And we're going to have to do it again.
Yeah,
For Z.
around, Z, yeah.
But see, the cool thing is like of all the forces that we see there, the 400 is going to do some work. The 80 and the 200 are not. The force of BY and BZ are not because they're both pointing right at that axis. So they're not going to do any work. What about over here?
You got the FAC doing work.
The FAZ is doing work. Why is the force of FAY not? Because it's in line with that axis. It's perfectly parallel, which is why it's nice to draw it good. Which incidentally is bothering me a little because I did not do that.
And it's 400 per line, right? So we gotta,
Yeah,
This is just nothing out of the side, but can you take the forces in the Z and the Y and create a matrix out of that to get the two variables?
my guess is you probably could, although off the top of my head, I'd have to think about. I mean, I don't think that's going to save any time, but yeah, it might create two equations, two unknowns, but we're going to be able to make one equation with one unknown. So I don't think it'd save any time, even if we could. So I've got 800. How far away is that from the Y axis?
1100 millimeters. But we- is
What's around millimeters? Oh, yeah,
it 1.1?
millimeters is,
Yeah, so milli is 1,000, so it'd be 8. If it's 1,100, it'd be 1.1 meters. So
We have to
you
do
could
that.
just
No,
ignore the
doesn't matter.
millimeters and just put them at the end, since
yeah,
they're all
you can totally,
millimeters.
you can do this with 1,100 or you can do it with 1.1. When I did it, I just left it alone, just left it millimeters. I think I will just because it matches the picture a little bit better. But 1.1 is going to make your numbers not enormous, what your mine are about to become. So I've got a force of 800, a perpendicular distance of 1,100 millimeters away. And that's trying to get it to go positively thanks to that little blue arrow. But then the force of AZ is actually trying to defeat that and therefore going in the opposite direction. And again, notice the distinction. It's like the force of AZ, but yet the axis is Y. Remember that whole cross product junk and how it was always, we had like a formulaic way of handling it. It was always like around the Y axis, there were no Ys. It was always Z's and X's. And so there is formulaic ways to kind of handle this. How far is it away? Looks like another 300, so it must be 1400. And that's it. Those are the only two forces. So that's a pretty good equation to start with. Even though there's 4 other forces that are unknown, I'm sorry, 3 other forces that are unknown, none of the other 3 are trying to get it to rotate around the y-axis. Spend some time so you can kind of visually see that. And so I now know the force of the required force of AZ. It is 628. I'm going to go ahead and switch it to newtons instead of, let's see. No, that's fine. No, I didn't do any rounding. It just is what it is. Yeah, 800 times 1100 divided by 1400. It's 628.6 approximately. So
This
So
is
cool.
Starting at point D.
I'm just finding reactions. I'm just trying to find out what job do those 2 supports have to do. And I haven't even started.
You wouldn't know the one.
The y-axis.
Yeah. And so that M of Y is the important distinction. Having that little Y there says it's not just some old moment, it's particularly around the Y-axis. And that's probably not a terrible idea, actually, instead of just writing a Y to say Y-axis right there, because it's not a point. Yeah, now let's do the same thing around the Z-axis. Let's see. Actually, this was even a little more particular to, I even kind of find myself wanting to even write a B in here. Do you know what I mean? Because it's like we chose to go over to the B location for the Y-axis. Do I need to do that? I'm actually not sure. I got to think about that.
Right, because A is not even on the y-axis.
Yeah, I mean, it's like the Y, if the Y-axis is drawn into the picture, then I'd say I don't really need to do that. So then, okay, cool. We got to go fast here. What are the sum of the moments around the Z-axis? So what do I have? Well, again, what's positive here? Like you kind of want to draw it in. Right-hand rule, this is a little easier. Thumb goes straight up. That's positive Z, so it's wrapping around toward me. There's no such thing as clockwise and counterclockwise anymore in 3D. That's why we got to think like this. So for me personally, it kind of helps me to go draw that in. So that's positive rotation. So that means, oh, that means the 200 and the 800 are causing positive rotation. So I'd have 2 200s, which is 400. And they're a distance of 150 and 150 through 700 millimeters away.
Talking about the 80.
Did I count that right? Yeah, I think I did. And then the 80 and the 80 are also trying to get it to rotate positive, and that's a total of 160. And they are 400 away from the Z-axis. And then lonely over there by itself, force of AY is trying to defeat it, trying to get it to rotate in the other direction. So force of AY. And it's all the way across again, just like last time. So it's 1400. And that's got to be 0. And that comes out to force of A in the Y direction, comes out to be 245.7 newtons.
So in this specific problem, it doesn't seem like there's any consequences if you were to move that Z and Y axis over to A.
Absolutely none. You're exactly right. You could totally move that Y-axis over to A now and redo this whole thing. Now, you know, the moments are more trouble. Does it make sense I could now switch to the forces of X, Y, and Z? Because I now have 2 of my 4 unknowns sorted out. And so I can now switch gears to see what's happening on the other side. Now, remember, if I was doing let's see, ultimately they said determine the internal loadings at C. Does it make sense? I have everything I need to draw the left side of this, and I don't even have to know what's going on over there if I don't want to. And given the fact that it's 220 right now, or a little after, I think I'm even going to skip that. I'm just going to draw that left-hand section right now because I know what's going on over there. So let's switch to the internal loadings at C. So, and this is where the free body diagram, you got to be really careful to kind of draw this correctly. So I've just got this pipe. I'm trying to draw this as good as I can. And I've got the force of AZ popping up here at 628. And I drew my arrows correctly because they came out positive, right? So that means I don't have to switch these different directions. And so there's my Y coming in at 245.7. So this, if you will, is kind of a left. I mean, it sort of looks like the left a little bit in that picture. So that's why I didn't have to bother to calculate the right. Now, here's where it gets kind of ugly. So I'm going out to C. So what else is missing? I got that. What else is missing since I'm out here at point C? I need that 800 in there, don't I? This is actually going down. So again, I'm trying to be careful. And by the way, I think I'm going to go over here to the side and kind of just remind myself, what are we doing here? This is positive Z. This is positive Y, and this is positive X. I'm trying to stay parallel to all those. So that's it in terms of actual forces. But remember, it is not broken at C. It is connected to something else. And so what do I have to draw in to get this correct then? This is what's kind of interesting.
Your shear, your moment, your normal.
Yeah, so let's get shear involved. Well, because there is a force in Z, does it make sense that this would be a shear in Z?
Why?
Well, just to maybe make your brain hurt less, so maybe I'll even switch colors here just to.
Just out of curiosity, why did you put the shear up?
I had no good reason.
You know,
Because now the conventions don't kind of work anymore because I'm all weird anyway. So I'm just picking it randomly. If it comes out negative, fine, it's negative. I mean, or I could redraw it. I could redraw it down and make it positive or whatever. But remember, I don't really care because shear is just.
Yeah, I just figured since we had that 800 going down, it'd be more likely to shear.
That's awesome. You got 800 down, 628 pushing up. Therefore, this is correct. Like I drew that correctly. Do you see what I mean? Because I got 800 going down and 628 going up. So that means this is what's going to be left over. So in a sense, I got lucky there. But that's not the only shear that I have. Don't I also have a shear coming in from this side over here? That'd be a shear in the Y direction. And I'm drawing that because of the 245.7. Don't I have shear going both ways? See, I can't, like, I got to do them separately. Now, interestingly, I could probably do Pythagorean theorem when I'm done to see how much shear is actually on it in some weird orientation, but I got to split it into its X and Y components, kind of like we did last term, or my brain's going to explode. So I got shear going in both places. Like last time, I think I'll draw this in black just to draw it in here. I've also got this normal force in the X direction. And I've even got this torsion in the X direction, but those are both going to be equal to 0 because none of those blue forces are doing anything to cause any of that again. So there's nothing twisting on this and there's nothing pulling it left and right. So those are both going to be 0 again. They will not be in question 27 on your assignment, however. What about our moment? Woo, okay, so moment, let's switch to red. So down here on this axis, I've got, and again, I'm not really sure which direction to draw this, but this would be a moment around the z-axis, would it not? So last time we just said m for moment, but now I've got a moment around the z-axis over there. And let's see. Yeah, I kind of got lucky there. That is the right-hand rule. So that was the positive version of it. I sort of drew it positively. But remember, there's kind of no such thing anymore in some respects. And then over here, parallel with the y-axis, let's see if I go y, this direction would be positive. That's the moment around the y-axis. Is that right? No, z-axis. That's the moment around the z-axis.
Drawing forces on forces. Lost the weeds now.
No, I'm sorry, that's y. This is not z, this is y. Everybody okay with that? Parallel, that axis is parallel to the y. My free body diagram is now actually complete. It's got everything in it. And so it's no different than we did before. It's just like you just have to do it twice. Like you got to do it once in kind of each direction.
We should be called Jedi. Dealing with so many forces.
This is insane.
Biggest dad joke.
Now, fortunately, as long as your picture's drawn good and you've done a good job of drawing axes parallel and so forth, this actually isn't very hard from here. So let's see if we can just pull this off really fast and get you guys out of here at a somewhat reasonable time. I'm going to keep trying to do this color coded. So let's do the vertical forces. So it's kind of like the sum of the forces in Z, yeah, maybe Z, some of the forces in Z. So that's kind of the up down according to the, drawing over here. It's kind of the up down direction. So don't I have 628.6 going up? And I've got 800 going down. What else is going up and down?
The shear force.
Yeah, the shear force, which one?
Z.
And Z, only Z, not Y. It's not going up and down, right? So it's only Z, and then that'd be equal to 0. So the shear force in Z works out to be 171, approximately.
Or would you, when you're doing this, would you just stay in one axis and do the momentum next on the axis?
That doesn't matter. It's up to you.
Or just do all the force?
Depends on your mind. I'm in sheer mind right now and like seeing stuff push different directions. And so I feel more like I should just keep going with this, except for which other direction am I looking at now?
Why?
Yeah, it's Y. It's like pushing along the Y axis. And so I've got 245.7. Is that positive or negative? Do you see why I drew this over here now? Because I can actually answer that, because it's like I decided to call that direction positive and I drew this in going negative. So that's actually negative. So negative 245.7.
Plus V.
And then Vy is the only other force going that direction, right? So that's it. So Vy is 245.7. Shear in the Y direction, 245.7.
What are these?
Moments, in red, sum of the moments. In this case, though, I do need to say at C, don't I? Because this is actually point C right here, because it's a very specific location. So it's actually at C, but around which axis am I concerned with here? I mean, I got some choices still, but
Aren't you gonna have to do both of them?
yeah, I'm gonna have to do both of them. Like they're, what kind of rotation are the forces that I see they're causing? And notice I'm very happy with choosing C because does it make sense? Vy and Vz are pointing right at it, so they're not causing any rotation. So I don't even have to include those. So it's like right here is moment Z. So there's one of them. So I'll pick that one.
Have more on, or. Let's do, you have the force on The 625 and the 800.
That's right. And that's causing rotation around Y. And so that's the reason it's kind of nice to actually write these in. Notice I called that moment around Y and moment around Z, as I should have, and therefore that's what I've got to calculate over here. You don't really have to have the C in this if you don't want to, but those are defined as around C. If I move to some different location, it's not going to be the same answers, right? Okay, so what's happening around the Z axis? So again, I got to picture that as vertical. So the 800 is pointing parallel to the Z axis. The 800 is not causing it to rotate around the Z axis. Neither is the 628. But the 245.7 is, and it's a distance of 500 millimeters. Yeah. Now, you guys were talking about, is it positive or negative? It's negative.
Use your hand, bro. I've been doing this for the last 5 minutes. I know it's positive, boy. Come on.
How?
So thumb straight up.
Yeah.
That arrow that I drew there earlier is what I'm looking at right now. I'm not doing the thumb anymore. I did the thumb to draw that arrow.
Yeah, that's fine.
So that's positive, and the 245 is going the other way.
Right.
So I'll erase this, but it's like, this is the axis we're talking about. Isn't this trying to get it to go that way? No, it's-
Rules is positive.
No, it's going against it. That's going against the red line.
That's your left hand, bro. Why are you
Oh.
using your left hand? My God.
Okay,
Steve's over here like, what's going on? This right hand rule is whack.
You can do the left-hand rule. You just got to stand on your head. We'll hold your legs if you want to go down that road. Okay, that problem solved. Good. So we got that trying to rotate, and then I guess that's it. Well, no. What do we have?
The momentum on Z.
Yeah, Z itself, the actual fact that it is connected to something else that's not letting it do that, right? Isn't it connected to a piece of pipe that's not letting it want to do that? It's no different than before. It's just mind blowing. So now here's where I suffer because I left 500 as 500 millimeters instead of 0.5 meters, because 0.5 times 245 would be like 120 Newton meters, and I'm going to get something like bazillion for this, right? So I'll write them both.
Should we keep it like?
I don't
guess,
care.
for consistency?
No, I don't care. Just look in the back and go, oh yeah, I guess my answer is the same. I don't care. So if all goes well, you get 122,850 for that. But if you leave the units in it, that 500 was millimeters and that 245 was Newton. So you have Newton millimeters.
122.9.
Yeah, exactly. 122.9 or 123 or whatever. 1.23, something like that, whatever, doesn't matter. 1.23 Newton meters. No, I'm sorry, 123 Newton meters, not 1.23. Millimeters is 1,000, so I moved the decimal point 3 places, so it'd be 123 Newton meters. And lastly, moment around C, but we said in the Y direction. And we've established with an arrow, I'm staring at this right now. I'm staring at this only. Oops, I didn't want to do that. I'm staring at this only for my direction positive because I already thought this through earlier, and I'm just looking at that and I'm staring at that 800 thinking, does it want it to go that way? And the answer is yes, it does. So it's positive. And it's a distance of 200, if I remember right, 200 and 300, yeah. It's a distance of 200. So 800 wants it to go positive. What about 628? Yeah, it's the other direction, and it's a distance of 500. And then we have the moment of Y itself, which is we defined as positive. So if I crunch all that in, I get 154,300. Newton millimeters, which would be better. I'm sure in the back of the book, it would say 154 Newton meters for this. It's not going to give that ridiculous answer. And I suppose it should be noted that N of X and torsion around X. Notice the normal force is in the X direction. So that's axially in this case. It's along the axis, so it's axially. There was no forces trying to do anything with that, so N of X better be 0. And there was nothing trying to get that thing to twist, so it also better be 0. So those are answers you'll see in the back of the book too. Those will be in there. Let me show you this really quick and we'll be done. If you have your book, you might look at question 27 because it's going to hurt your person. But it's a good question. But you're not just going to sit down and do it. It's like what we just did, but it's actually got all 3 axes. It's got torsions that aren't 0. I'm actually going to post this for you. I stole this from the, and I'm doing this because we didn't spend lots of time on this, but this is actually the author's really nice. This author is, if he actually did his own drawings, he is an artistic dude, because that's freehand. But notice that's the proper free body diagram that we just drew, except for we just drew only had 2 dimensions because there was really nothing happening in X, but notice he's got stuff happening in X, Y, and Z here. And so here's the pipe. It's split right there. That's where the break is, and that's where he drew the axis in. So he's got X over here, Z up here, and Y going back this direction. And so do you see how this is torsion? He's got a really nice drawing of an arrow there. That's torsion at B. This is location B, and it's around the X axis. Do you agree with that? Do you see how I was looking at that labeled correctly? And then down here, this is a moment rotating around the Z axis. So he called it moment around the Z axis. So it's spinning around that axis right there. And then this is shear at B in the Z direction. So that's aiming in the Z direction. Over here is shear in the X direction. Over here is shear in the Y direction. Except for, no, he called it normal, not shear. Notice that's interesting. I kind of got in a hurry. He called it normal. At first I thought he made a mistake, but isn't that in the direction of the axis that the pipe happens to be? So instead of calling it shear, because that's not going to be shear, shear is this way, normal is this way. So he gave it a totally different name, didn't he? And yet those are all the forces going in those directions. 2 of them are called shear, 1 of them is called normal.
So is there a normal anywhere else?
um,
Kind of like in line with the pipe, but I'm not seeing one when it goes into the Z-axis. Like I would think there'd be a normal.
well, it's got to be parallel. It's parallel to the way that the linear piece that you're chopping. If you decide to take this pen and chop it right here,
Oh,
then automatically a force in that direction is called normal. A force in this direction is called shear. Because of the nature of what breaks it, and because material strength wise, some things break more easily in shear than they do in kind of tension, a normal force. And so that's why the distinction. But notice this joint over here is connected not just to a horizontal pipe, but one that turns vertically. Therefore, these 300 and 400 are going to try to get that whole pipe to rotate around that point now. And so it's going to be complicated. So you've got 300 up here, 400 here, and then you got this 500 that's coming down at some weird angle defined by a 3, 4, 5 triangle. And so you've got all kinds of calculations to make. And then the other reason I included this is in your problem, it says that it had 12 kilograms right here, but remember, kilogram is not a force. So you have to take 12 times 9.81.
And that's the center of mass of that rod.
And it's 2 meters long. So it's kilograms, it's 12 kilograms per meter. That's how much the bar weighs. And that part of the bar is 2 meters long. So it's 12 kilograms per meter times 2 meters times gravity. And now that's actually newtons. And that N right there is newtons, not normal force. So that's
This is
kind of
where
annoying.
it confuses me, because I would also apply that to the portion that's going out.
That is applied to it. So right here, this is also 2, and it's exactly the same thing. And so he has the same calculation. He has the same calculation right here, and he just aims at this force. There's that arrow right there that says this whole thing weighs that amount.
Oh, per meter, yeah.
And then he also has the same thing coming down here because it just happens to be the same weight.
for the fourth.
I accept your challenge, Doug.
Challenge accepted.
Challenge accepted.
You have everything you need to do that, but you're just in a different world. And so the first few questions in your assignment aren't too bad, but you have one that's just like that pulley one we just did that had the three pulleys that we did together. There was like a question 7 and 8 to it, or 18 and 19. I did 18. You have to do 19. Do that one first and save 27 for last. 27 in a sense will be the only problem that's genuinely hard, but you can do it. It's just painful to your brain.